Okay, this is going to be the last video of the week. Okay, so this one will be for Thursday. Again, there's a possibility I'll be back before then. If so, go ahead and watch the videos in any case, but there may be an actual Q&A session or help you with homework or whatever the case may be. Okay, so let me go ahead and get my iPad up here shared. Okay, so this is on chapter 10, the last one of the week. It's on sorting algorithms. Okay, so this chapter again is going to be a preview of what you're going to see again when you take the algorithms class, which is the next class in this sequence. Okay, and sorting's a big problem, right? It gets done a lot. We're often sorting things because searching's quicker, looking for repetitive items in a table is much quicker when things have been sorted. Okay, so sorting is very important. So the method you use for sorting can be important. Sorting is going to vary performance-wise a whole bunch. Okay, so again, the idea for all of these is we're going to start with an unsorted list. It's not ordered. We're going to end up with one that is ordered. Okay, and there are lots of them out there. The book starts with the idea of a selection sort. Okay, and the selection sort, it starts this on page 534. Okay, it's basically going to go through the unsorted portion of the list, okay, and find the smallest item that's not. Okay, so again, we've got our list. Okay, so when it's first there, we don't know where that's at. Okay, we don't know the smallest item, so we have to go through each one here to 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 here. This is the king of the hill algorithm we've been talking about. Okay, then whichever item is the smallest one. So let's say in our list here we've got a 14, 3, 18, 2, 21, 6, 47, 15, 9. Okay, it has to go through all of these to see that the smallest one is this 2. Okay, once it finds that, it's going to swap, okay, with the first position. Okay, so it's going to put the 2 over here. It's going to leave the 3, the 18 alone. It's going to put the 14 here, and so forth all the way down. Doesn't bother the rest of them. Okay, and now it's going to mark that this is now sorted. Okay, and then as it goes through with each step, so that's after one run through, then it's going to be the next one through and so forth. It's going to one by one go through and sort. Okay, so it gives you the code for that, and it's starting on page 536 on finding that the minimum and moving through that process. Okay, so it turns out this is not the most efficient algorithm that you can get. Okay, because if you have like 100 records, then the first time through you have to look at 100, you have to look at 99, and then 98, and so forth. Not super efficient. Okay, so the other way to look at this is that we can do an n-1 for the first time times n-2 all the way to looking at 2 and then finally looking at 1. It's the same thing more or less. Okay, and again, in algorithms class, we'll talk about how to use a simple little formula. We get to 1/2 of n times n-1. Okay, when you multiply this out, the big things we care about here is the n times n. So this is going to give us the big O efficiency of n squared. Okay, it's not the worst algorithm in the world, and certainly it is better than some. The worst one you never want to do, it's called a bubble sort. It's bad. Don't do it. It's sometimes used as an example of a bad sort. Okay, and we won't go into it because it's so bad. Okay. So this, if you don't have many to sort, it's relatively simple to envision. Not really that big of a deal. Okay. So the next sort we talk about is going to be the insertion sort. Okay, so the insertion sort, what it's going to do, okay, it's going to go through the list and try to find the position where things go. Okay, so it's going to, let me see if there's a better description here. It sorts a list by moving each element to its proper place. Okay, so we start by putting the first item in the first place, second item in the second place, and so forth. Okay, so there's a pseudo algorithm on page 541 that we're going to start for the first out of order item equal to 1. As long as it's less than the length, we're going to go up each time. And then if the list at the position first out of order is less than the first out of order minus 1, you're going to copy that item into temp. You're then going to go through and find where that item goes. Okay. So it's similar in some ways to the selection sort, okay, but with a little less messing around. Okay, there's an implementation of that on page 543. Okay, on how that works. Okay, it then goes through a fairly detailed example starting on 544 on the insertion sort with the linked list based lists, and goes through how this may work out for us, including the actual code for that. Okay, so it turns out that the insertion sort, okay, is also going to be at big O of n squared. Okay, but when you look at the number of swapping, when we're comparing it to the selection sort does swaps n times, where the insertion sort does swaps in n squared times. So actually the insertion sort is not as good in that sense. Okay. The next sort we talk about is the shell sort. Okay, so the shell sort starts with the insertion sort, but it's going to modify it. Okay, it was introduced in 1959 by this DE shell. That's why it's known as a shell sort. Okay, it's also known as the diminishing increment sort. Okay, so in this, we're going to look at the list. It's going to look at sublists at a particular distance. So each sublist is sorted, okay, so that the items that are far apart move closer to their final position. Okay, so we're going to basically subsort groups of the list. Okay, so if we have our list here, however big it is, the shell sort says you're going to sort this bit first. Then we're going to sort this chunk, and then that chunk, and then that chunk, and that chunk, and then that chunk. Each of the smaller chunks will sort more quickly. Okay, then you're going to start combining those together into bigger sorts, and then finally the whole thing gets sorted. Okay, so it's kind of the idea of a divide and conquer element. Okay, so it talks about that. It gives an example of how you can implement that function on page 550. Okay, and then this next section talks about the lower bound on the comparison-based sorts. Okay, so if you look at the problem, and again, that section is just a page and a half. It's kind of a preview of algorithm, so don't sweat that too much. But the lower bound just means the fastest that a comparison-based sort can be. Okay, and it goes through that math for you, and it turns out that the best you can do. Okay, so the best comparison-based sort is in the big O of n log n. Okay, and the log here is assumed to be base 2, binary log. Okay, so that's the best it can be, and that's because of the amount of information that needs to be processed. Again, that's a topic for algorithms class. Okay, but the two sorts that you most often are going to see, okay, are the two that we end with here. Okay, and those are the quick sort and the merge sort. Okay, and also the heap sort. Heap sort somewhat. Those are the big three. But heap sort tends to be a little less effective. Okay. So let's go through the basic ideas here. Okay, so with the quick sort, So these are the sorts you really care about. These are the sorts that people assume on a job interview that you understand how these work. Okay. The quick sort comes down to this. If the list size is greater than 1, okay, we're first going to partition the list into 2 sublists. Okay. And by partition here, we're going to take some random value. Okay. So here's our list that has, I don't know, numbers of some sort. Okay. We're going to pick some partition factor, whatever you want to call it, of say 50. Okay. With our range of numbers, we think that makes sense. Okay. We're going to divide it up, and it may not be even. So somewhere we're going to divide up those that are less than 50 and those that are greater than 50. Okay, so that's the idea. So we're going to partition. It's not a sort, but it's a rough sorting. Okay, greater than or equal to some value. Okay, we're then going to recursively do a quick sort on this lower sublist. Okay, and then do a quick sort on the upper sublist. Okay, and then finally we're going to combine them. The sorted lists into one. Okay. So again, it's a divide and conquer. We're going to divide it up based on this partition, and then we're going to go through. It gives an example of this on page 553. So again, in their example, we've got a 45, we've got an 82 in the second position, we've got a 25, a 54, sorry, 94, a 94, a 50, a 60, a 78, a 32, and a 92. I ran out of room. Okay. If they pick again, like I did, a partition of 50. Okay, so this is our main list. Okay, then the lower would have in it the 32, the 25, the 45. Okay, that's all that's in the lower. Then we have the 50. The upper would contain all the rest. Okay, the 82, the 60, the 78, the 94, and the 92. Okay, these again are not sorted, neither one. Okay, but these are all less than 50. These are all greater than 50. Okay, then each of these will be broken down by a different factor. Okay, and often to find the partition, you'll just take the average of the numbers. Okay, so that's what quicksort looks like, the general idea. Again, it's going to give some examples that are worth going through. It's good stuff. And then there'll be a partition code that it gives you. Okay, and then finally the quicksort there as well. Okay, and it turns out that on the average case, okay, so for quicksort, the average case, as far as the number of comparisons, is going to be at our big O of n log n. Okay, with the worst case being big O of n squared. Okay, so not bad. The next sort we care about is the merge sort. And what the merge sort does, it's going to repeatedly break the list into half, divide it, keep dividing it till there's just one, then pull it back together. Okay, so if we have the following, if we have our list being 35, 28, 18, 45, 62, 48, 30, and 38. Okay, we're going to divide it up into 2 groups. We usually put boxes around all these. I'll just do the one side. Okay, so we have the 35, the 28, the 18, and the 45 in this group. Okay, divide that up again into the 35 and the 28 and the 18 and the 45. Subdivide again. These are recursive calls into the 35, the 28, the 18, and the 45. Okay. We now start building them back up. Okay. So to build them back up, these two are going to come back down into, we're going to put these in order. Okay. So we're going to put the 28 here and 35 there. Okay. This one, we're going to put the 18 and then the 45. Okay. We then go and look at this one. The 18 comes first, then the 28, then the 35, and then the 45. Okay. And we expand back out. And all that's on page 559. And I said half of it, but that's the idea. Okay. So we're going to divide them up. Then we're going to put them back together. Okay. We break them up, then we merge them back. So there's code for all of that. Okay. The analysis of this. Okay. So this is also in its best case an n log n. Okay. Or in the average case. Okay. But the worst case there is also n log n. Okay. So this one, the average and worst is n log n. Big O of n log n. Okay. So it's a good one as well. So you'll see quicksort and merge sort used a bunch. Okay. Then the last sort that they talk about is the heap sort. Okay. So the heap sort has at its heart this idea of a heap. Okay. A heap is a list in which each element contains a key such that the key at the element position of k is at least as large as the key in the element at position 2k plus 1 and 2k plus 2. Okay, so it's not sorted, okay, but something like this. And that's also known as the heap property or the parental dominance. Okay, we have 85, which breaks down into a 70 and an 80. Okay, and then we have that break down into a 50 and a 40, 75, a 30, a 20, a 10, a 35, a 15, and a 62, and a 58. Okay. And this would be, the original would be 85, 70, 80, 50, 40, 75, 70, and so forth. Okay. We're going to break it down this way. Again, this has the heap property in that, of parental dominance. This is the biggest in the entire list. Okay. This is bigger than all of its children. Okay. This is bigger than all of its children. Same thing. Okay. This is bigger than all of its children. Okay. This is bigger than all of its children. This one doesn't have children. Okay. But the list is not sorted at all. Okay. But we're going to use this idea. What really matters with the heap sort here is that this is the largest. The root is the largest. Okay. So the idea behind the heap sort is that you're going to build a heap first. Okay. So the steps here to the algorithm, on whatever data you have, you're going to build a heap, which basically puts the largest on top. Okay, you're going to then remove that, or put that someplace else, remove the top into position. Okay, so again, we're sorting things. We do our heap. Over here is where the first one goes. Okay, then you're going to reheap, basically. Okay, you're going to make a heap again, and then again pull the top one off. So that's how that's going to work. Okay, there are examples of that in the book using binary trees, which we haven't really talked about yet. So it's interesting they're bringing this up now. That's going to be coming up later. Okay, and on these, the best case scenario, or the average case here, is going to be an n log n as also. Okay. But the worst example here is going to be an n squared. So which one you use depends on a lot of things, but all of these are reasonable kinds of items. Okay. The last thing this chapter talks about is going to be quite an example on this on priority queues on some of the election results. Okay. And again, priority queues are an important data structure. It's worth going through and looking at that example. Okay. And that's going to be it for the week. Okay. So again, at some point, I expect that I will be up. I should be up every day, with the possible exception of Monday. I should be up for text. If you want to text me, that should not be a problem. Okay. I may come back for a live Zoom session later in the week. We'll have to see how it goes. Okay. It's unknowable at this point. Okay. But if you have questions, certainly send me a message and I will get back to you with the answer. Okay, so that's it. So I hope you guys have a good week.